wavelets, and 180 pulse in a heteronuclear domain, diverge them as they were, because this is a simple question of relabeling. Relabel kar rahe hain aap. And when you relabel them, they move apart from each other. They are anti-phase to each other, right? Anti-phase to each other. They are anti-phase to each other. And they are anti-phase to each other on X axis. Now, if you bring your radio frequency oscillator shifting to Y and give it a, what will happen? Right hand thumb rule that the one which is here will go down and the one here will go up, and you would have a situation like this, right? The magnetization vector, this resulting magnetization vector, was always the two component, the carbon, beta carbon. What we have done, that you have created a situation from here to here in which you inverted one to the, this is one line inverted to the negative Z as compared to this. This Z, this magnetization vector has a two magnetization, because proton is seeing the carbon into situation. Therefore, actually there are two magnetization, because they have a two different precision frequencies, same reason of alpha and beta. Always remember there are two, and they are phased. They so-called phased and together magnetization vector. But when you create a situation like this, inverted one component into negative component. Okay? Line of proton is inverted. What you have done? One line of proton is now inverted. Now this pulse is called SPI, selective population inversion. Population inversion, okay? And this is the crucially important pulse. Now remember, at this point of time, when this is your magnetization vector for carbon, which is your nuclei of interest. This is the one you want to read. When you provide ATX pulse and in carbon domain, आपको ये सारी चीजें अपने ज़हन में रखनी पड़ेंगी, right? 180x pulse in carbon domain, this moves this to negative Z, okay? Negative Z. Exactly at this point of time, 90Y has also been provided, which is your spin echo, so-called spin population inversion pulse. This spin population inversion pulse add into this a component which was not present. Okay? A component which was not present, and therefore you create a situation in which a part of the proton is now added into the population of carbon, right? This is the situation of selective population inversion. What you have done, you have added a part of the population of proton into carbon. There was no, इसमें यहाँ पे there was no component on the Z positive side, right? And therefore you create a situation in which you have an added polarization transfer in the domain of a carbon. Now it's fairly easy. If you want to read, you have to bring it to the XY plane. And how you can bring it to the XY plane? Pulse or 90 pulse will bring them at a different position, but 90Y pulse, When you give a 90 Y pulse, you create a situation like then you detect your signal. Okay, and this, kindly remember, is increased because of this selective population inversion. कितने लोगों को इत्मीनान क़ल्ब हासिल हुआ है? How many people have got only one? What is the Arabic word for piece of Sakinatul Qalb, huh? So, huh? वो तो अल्लाह के जिक्र से ही हासिल होता है, मैं कभी ये समझ लें तो शायद उससे भी You see, this absolutely fascinating understanding vector in its fate is the result of certain action, is certainly a God-giving, God-gifted understanding. सही है? तो हमें हर चीज में अल्लाह पाक का शुक्र अदा करना चाहिए. अल्लाह के शुक्र की जो फवायद होते हैं, इसके लिए क्या बात करें?
ये पॉपुलेशन इन्वर्जन एंड इम्पल्सेस और ये सब चीजें कर क्यों रहे हैं? To avoid what thing? थोड़ा सा.
I don't know why increase in population would embarrass me because I have not contributed that much. But I can tell you, see, you are doing this polarization transfer because you want to increase the intensity of carbon. Okay?
मतलब वो जो peaks which are not visible are very poor under the ordinary circumstances. They can be made visible with this technique.
Yes. And it is extremely. Gee, you see these two different situations. This is the situation when you just consider a gyromagnetic ratio, right? But please, abundance is very, very low. So this peak would be 60,000, 6,000 less intense as compared to proton. 6,000 less intense. And a slight increase in sensitivity is a most desirable property which every NMR spectroscopist would like to achieve. ठीक है? शक हो तो I can even try my luck again. Yeah? That is an interesting thing actually. Remember, the AT experts, if you go into the books, it's not really very, it's not included in most of it. But in reality, there are two 180X pulses. 180X pulse is in proton domain, right? Proton domain. This is a spin echo pulse, which create a mirror image situation. And this is used for controlling or eliminating the so-called magnetic inhomogeneity and the chemical shift effect. This one in the carbon domain is given for converting this into a negative magnetization vector. Kindly remember that 180X pulse in carbon domain also have effect on proton. They are scalarly coupled, one affect the other, because 180X pulse would switch the population to a different domain. As a result, these counter-rotating magnetization would continue to away from each other, antiphase. And situation is required in order to have a 90 Y pulse. this 90 vipers. And remember, in 90 vipers, 90 vipers after this 90 vipers is called a spin inversion pulse, because one component go into Z plus and the other Z negative. Remember, they were together here. They were both component of proton. Always remember that although we show a bulk magnetization combination of many vectors together, in this case there are two magnetization vectors. One is coupled to beta carbon and the other with the alpha carbon. By doing all this jugglery, you actually able to transfer one to the, you separated them together. And this anti-phasing, this is the population inversion, because you change the sign of one component of the doublet into antiphase. And this particular situation is sharing the energy level with the carbon, and therefore this adds into this, and that is precisely what we have done into an spin echo inversion. And that is the addition of this population transfer into the carbon, and you get the enhanced signal, right? Koi masla? That the fully coupled carbon-13 would appear as a doublet, decoupled would appear because of the result of collapse of these two signals into one. So you see you have a gain of intensity on the intensity information. This is the polarization transfer in sensitive nuclei enhancement by polarization transfer, in which you have a plus and negative peak, and this is a substantial there are phase cycling methods available through which you can convert the distorted peak into a positive peak. Is called refocused inept, and refocused inept decoupled to have a refocused. Now you compare the intensity of this with this with decoupled thing, and you see there is a substantial increase in intensity polarization transfer because of polarization transfer. And you can also compare the intensity of this doublet with this doublet, and you see even the refocused inept would give you an increased sensitivity. Now, polarization experiment have been numerous. People have developed polarization. Kindly remember, whenever there was a problem, for instance, in this case, there was a problem of distorted. People were trying to solve the distorted peak by using refocusing thing. There was also one more problem, and I want you to think over it. You see, I told you last time that there is a SYNAPT, selective enhancement by polarization transfer, that you have a large molecule and then you can give a pulse to a selective pulse to only one proton. And when you give the coupled carbon increase in sensitivity, right? So you can have a selective inept too, or you can have a broadband inept in which you have a radio frequency oscillation which transfer the population of 1/2 of all the protons present in the sample. So you get a selective inept, or you can get a non-selective inept in which you have a population transfer into the carbon, which is insensitive nuclei. One of the most important polarization transfer is called depth, distortion by polarization transfer. is an excellent technique. You can compare what it is actually. Let's see that this is the decoupled spectrum in which carbon as well, right? You see quadricarbon, this quadricarbon, this quadricarbon here also, this quadricarbon. In the polarization transfer experiment, you don't see any quadricarbon, and the reason is very obvious that there is no polarization transfer, there is no proton polarization to the attached carbon. Therefore, is primarily a broadband decoupled C13 NMR spectrum minus quadricarbon. This depth 90 is a situation in which we have only CHs, and depth 135 is the situation in which we have CHs and CH3s on the positive phase and CH2s on the negative phase. So it actually solves your problem of multiplicity. The whole fully decoupled to all these three variants of polarization transfer is called ADAPT, audited distortionless enhancement by polarization transfer. Audited because you audit one into the other, you carbon from their absence in depth 45, and then you recognize CHs by recording a depth 90, and then you recognize the CH3 and CHs by recording 135. So you see, by using this technique, quadricarbon, CHs, CH2s, CH3s, all four different types of multiplicities of carbon can be recognized. Important technique called distortionless enhancement by polarization transfer, and this is an excellent technique. For instance, if I tell you that if you have a molecule like this, and if I invite you to think what are the quadricarbon at 170, about 175 or something. 5 is lactone carbonyl, right? Is an ester carbonyl. Okay, and then you have another quadricarbon, which is this carbon, or this carbon, perhaps this carbon, right? This carbon, and then you have one more quadricarbon. I'm sorry, this one quadricarbon is for this, right? One is for this, and then you have one is a simple aliphatic quadricarbon, and that is this one. So you identify all quadricarbons. This is perhaps somewhere in between, which you would be able to see somewhere. I don't know where it is. Perhaps somewhere in between. So you identify all quadricarbon. Now CH2s. How many CH2s? 1, 2, 3, 4, 5, 6, 7. कितने हैं? 7 है. 3, 4, 5, 6, 7 should be the most downfield one, isn't it? CH2. So this is this CH2, and all well spread, and you can recognize them. These would be very close to each other, and therefore be this one, and these CH2s next to an OH. Next to OH would be the down. So you recognize CH2s. On the other hand, CHs, if you have a CHs, so you go for 90 CH, 1, 2, 3, 4, 5. And CHs are 1, 2, 3, and 4. So you have, there is any 5 also? 1, 2, 3, 3, and 5. These are 4, 5. These are, which one is going to be the most downfield among the CHs? This one, right? The most downfield because it's an olefinic CH. And these four are this one, this one, this one. This one would be the second most downfield, and that is this one. Okay, and this would also be these, both of them are perhaps this one and this one and this one. So you can easily recognize. With this, you would be able to recognize that there are how many methyls? 1, 2? Two methyls, right? And these two methyls are this one, and because these are not present here, right? CHs. So you can recognize methyls too. Okay? You want to interpret that again? Is it of any interest to you? No? Yes, no? Yes. This is your fully decoupled, and when you minus this fully decoupled C13 NMR spectrum with depth 45, remember 45 is an angle. Kindly remember 90 is an angle also, and 135 is an angle also. Remember, this is translated into a delay. Kindly remember that I showed you this diagram. You remember this diagram? This is an apt diagram, and this is exactly the same thing. That a particular time delay you can see certain things, and at a different time delay you see the other. So they are nothing fancy, absolutely very easy understanding of the spectrum. Interpretation is extremely facilitated by the fact that now you can distinguish between quadricarbon, you can distinguish between CHs. This is a very clear CH2 domain, and then you can recognize the CH3. So you can interpret the whole results while you see the singlets, while you have a singlets with sensitivity enhancement because of polarization transfer. You also, what was the problem? Problem was you wanted to have a C13 NMR spectrum with greater sensitivity. You wanted to have C13 NMR spectrum which appear as a singlet, and you wanted to have C13 NMR spectrum which provides you multiplicity information, and that's what you got.
Excuse me, sir.
That is an amazingly spectra.
Excuse me, sir.
Which you get quadricarbon, in which you get CH2s, in which you get CHs and CH3s. So you can in all four different types of multiplicities of carbons using a very interesting routine called polarization transfer. Polarization transfer, kindly remember that this is a novel pulse sequence. It is independent. It is independent of the data processing. It is a novel technique through which you transfer of more sensitive nuclei, and as a result you increase the population difference between two energy levels of less sensitive nuclei, population difference, and as a result you get a more sensitive nuclei. It is a general technique. Inept or depth is now become the component of a very large number of. Wherever you need to have sensitivity of carbon increased, you use inept as. Don't even mention the whole sequence. You just say inept. You say inept, inadequate, inept HMPC, inept HMQC. When we will learn the inverse NMR spectroscopy, you will learn that exactly the same philosophy. When you transfer the polarization of a more sensitive nuclei to less sensitive nuclei, and you get a greater sensitivity, There is an inverse experiment also in which the population of less sensitive nuclei transfer to more sensitive nuclei. And why we would do that, why somebody would like to do this, is a question which we would always remember that in modern NMR spectroscopy you the carbon now. You rarely detect the carbon now. You always try to detect the carbon through its effect on proton. You detect the proton. Exactly the same analogy as you don't see a person, but you see a person in a mirror, and mirror is proton. So you monitor the carbon-13 in proton, which we will understand as we will proceed further. Now I want to take you further to a very interesting technique, but just for the sake of understanding, this is the proton NMR of a molecule menthol, and you see there are a number of peaks. Is an experiment. Inadequate is an experiment which is if it can be made sensitive, this is the only technique which people would ever use, because this provides you information about carbon-carbon coupling. Remember, all and most chemical molecule by chemicals are the framework of carbon and carbon, and try to attempt is to make the connectivity between carbon and carbon in the first phase, and then you go for the geometrical information or confirmation and configuration. So inadequate, incredible natural abundance transfer experiment is an interesting technique in which you discover carbon-13 coupling, exactly like you have a proton-proton coupling. Difficulty, philosophy is you are trying to discover. Thank you. Thank you so much, Shukriya. I showed you that proton NMR looked nice. These are proton-proton coupling. All protons are very sensitive. All protons are abundant. All protons are NMR active. But if you need to record the C13 spectrum, what would be the problems? Philosophy exactly the same. Philosophy वही है जो proton-proton coupling की होती है. Carbon-13, what would be the difficulties? If you can record a carbon-13 NMR spectrum, that's what you need. To be honest, you don't need anything else. Why you need to worry about proton-proton coupling? Proton-proton coupling would never give you a structure. Proton-proton coupling would give you which proton is which close to the which proton. But it will never tell you protons are not. Always remember, protons are not connected to each other. That is the corresponding carbon which are connected to each other. So you get indirect coupling between proton and proton. You do a proton-carbon, and then because you cannot detect the carbon is a problem. And why you cannot detect the carbon-carbon coupling?
Yes.
Why? Chances of what? I think we are in a very interesting stage of discussion. Is any need of a carbon carbon-13 coupling. In order to have a carbon-13 coupling, you need to have a carbon-13 spectrum, right? And for a carbon-13 spectrum, ये खुद ब खुद चलता है क्या? It has a mind of its own. Okay. For instance, if you have F, and if you have all three carbons of ethanol as the spectrum, carbon-13 spectrum with no coupling with the proton, how it would look like. Ethanol with 2 methyl NCH2 carbon-13. Huh? 2 doublets at their chemical shift values, right? Because they are coupled with each other. Carbon would exactly identical manner as you see a proton-proton coupling. Remember, these are spin half nuclei, so they will appear as a doublet too. This is the end of it. This is the end of NMR spectroscopy, dilute spin of carbon-13. Problem is that you can't do it actually because of a simple fact that 100 carbon, so if you have a molecule of 100, all of them would have C13 isotope, will be a C13 isotope. So for example, if you want to record carbon-13, each carbon of this molecule need to be carbon-13. So at least randomly kitne molecule at one carbon-13 spectrum? 10,000. 100 molecules of 100 carbons. Agree? Just one isolated carbon-13. Okay? Is it? You delete all others. Yeah. This one? So many. Ouch. बुला लीजिए उन्हें. I think मेरे ख्याल में आप बाकी सारी डिलीट कर दीजिएगा. हाँ. Slow. What is the problem with it? Not anymore. Okay, so the problem is primarily problem with the computer or presentation बाहर दी है? इसके आगे बढ़ ही नहीं रहा. Don't worry about that. Finding two together, see, in order to have a fully coupled C30 NMR spectrum, like you have a proton spectrum, means primarily that all a molecule need to be C13, right? Can you do that? Can you synthesize a molecule in which all carbons is C13? क्यों नहीं कर सकते? कर सकते हैं, है ना? You can do organic synthesis with molecules which have all carbon 13. कर सकते हैं ना? There are techniques available in which you can produce fully labeled carbon 13 molecule. Right? I want to have cholesterol in which every carbon is carbon 13. What you will do? Little biosynthesis. I want to isolate from my cholesterol every carbon of cholesterol as C13.
सारे precursors ऐसे related to carbon.
Precursor, is it theoretical? Huh? Is it theoretically possible? Remember, what is the carbon source of a plant? Carbon dioxide. And can you have whole atmosphere of the world carbon 13? Reason why it is absolutely impossible to biosynthesize all labeled carbon 13 de novo in plants is not possible. But you can do it synthetically. You can do it by conventional method. You can synthesize molecules. Now, in order to synthesize all labeled molecule, you need to know the structure of the molecule. And if you know the structure of the molecule, why you want to do that, right? You don't want to do that. So it's not really very physical. I tell you that the carbon 13 labeling is actually used as a very important tool in biosynthesis. You would recognize the importance of carbon 13 labeling. For instance, if you try to piece are synthesized from a very simple molecule called isoprene. Isoprene is synthesized by mevalonic acid, and mevalonic acid is synthesized by acetoacetate. Acetate is synthesized by acetic acid. So if you introduce a labeled acetoacetate into the roots of a plant, a label, let's say carbonyl group of acetoacetate is C13 label, and if you want to know the process of a biosynthesis, then you isolate your compound And if you find that while recording this C13, and you have a big huge peak of one carbon, then you would know that your acetoacetate is the precursor of that molecule. Because incorporation of carbon-13 in your resulting compound is the proof that your precursor acetoacetate is the precursor of that particular molecule. So all biosynthetic studies today are conducted not by radioactive label, because there was a time when people were actually labeling the precursors with radioactive C14. Because now techniques available in which we can have any molecule introduced into the root of the plant or cell culture of a plant also, and at the end of the day you isolate a compound and you find that certain in the molecule are carbon. When you record a carbon-13 spectrum of this molecule, there would be certain peaks very, very big in size. कौन सी peaks होंगी? Which peaks would appear as very big in size?
C13.
Which are labeled, because as compared to natural abundance, they are 100% there. So in C13 NMR spectrum, a few peaks will appear as very large, which represent that the precursor was incorporated in the secondary metabolism or secondary metabolized or whatever. It is a standard technique. This is a you carry out a biosynthetic studies. Very, very easy. I have seen this in Professor Zank's laboratory, who is a Nobel laureate in biosynthesis. And what they are doing, actually, they have a small little plant. They cut a small section of the stem, the small section, and they have a small beaker, 1 ml beaker with labeled precursor. And labeled precursor can be two types of labeled precursor. Either can be radioactive labeled, because when you have a radioactive labeled precursor, it's so easy. You isolate a compound and you go to beta, which you can read the radioactive labeling. But more often now, there is no radioactive use. 13 is a stable isotope. So they have a small trunk of this, small portion of the trunk soaked in a small beaker which contain C13 labeled precursor. And after a certain period of time, they crush the plant, they isolate the compound, and then they carry out a C13 NMR spectrum and they see a label. When they see a large peak of C13, they say this is the biosynthetic precursor. They don't see any carbon-13 in the resulting compound. They say this was not the precursor of the carbon-13 of the particular compound. So biosynthetic studies, carbon-13 labeling is actually used in a very intelligent way. Now I want to ask you a question, that possibility of having carbon 0.1%, but if you have a situation in which you would like to see two carbon-13s together, one after the other, the possibility is 1 into 10,000, right? 1.1 into 1.1, the possibility of having two C13s together, 1 in 10,000. So one molecules would have carbon-13 next to a carbon-13. And if you want to have the other is 1 in a million, right? So the possibility of having two carbon-13s neighbor to each other is so rare that you cannot record a normal carbon-13 spectrum. Now I want to challenge you, and I want to challenge your understanding of NMR spectrum. You see, in a molecule, you have C13, 1000, and in every molecule there is one C13, right? The C13 labeling. C13 coupled with C13 is a doublet, right? Possibility of having C13 next to C13, C13 next to C13 is 1 in 10,000. So if I draw for you, these three peaks, this is called satellite peak, right? And this is main C13 peak. This represent C13, right? Understand that you have 1 in a 10,000 molecule next to, and this peak belong to what? Single C13. Can you see that? Can you see that, right? Or light chalane ki zarurat hai. So you have a very big peak which represent the isolated C13 and a small side bands satellite peak which represents C13 to C13. And if I tell you that I want to delete this and I just want to see this, what do you need to do?
The radio frequency oscillators.
I don't want to see the big peak. I don't want to see the big peak which the C13, isolated C13. I just want to see the satellite peak or a coupled peak for a situation in which we have carbon 13 next to a carbon 13. What you would do?
Sir, उसका radio frequency का oscillator on करें.
Can you somehow separate this big huge isolated carbon 13 peak from the tiny little doublet which is representing C13 next to a C13? Can you do that?
Sir, radio frequency
Answer is so trivially simple, very, very simple. And you would then appreciate how important it is to understand the diagram. So carbon 13 head to nuclear shift correlation spectroscopy is inadequate. Homonuclear, because carbon 13 incredible natural abundance double quantum transfer experiment. Incredible means very low natural abundance 13 next to C13. Abundance means they are the abundance in nature, but when you label it, it's not natural abundance. They call labeled spectrum. And chances of finding two carbon 13 nuclei connected to each other is 1 in 10,000. To detect such a weak interaction, this doublet, it is necessary to suppress the 100 times stronger signal from the molecule with C13 nucleus. You would never be able to see this doublet in the presence of a big singlet. Although in all C13 spectrum, if you really go and ask them to record for you a spectrum, and you ask them to amplify the signal, see these small satellite peak in around the big peak in every spectrum. If you have a very concentrated C13 NMR, if you have a very concentrated sample, you would be able to see these satellite peaks even more prominently. But you cannot appreciate these satellite peaks suppressing the most important challenge. I want to take you a very simple experiment. 90 X pulse, everything together. One C13 without any neighbor as a C13 and C with a C13. It is split into three parts. The center one is representing the isolated C13 and the two are representing the C13 because of the neighbor C13. They are counter-rotating. They are rotating away from each other. So there would be a situation in which you would have this doublet antiphase to each other. When it is in this situation, what you would do to eliminate this big peak?
Z-axis. So Z-axis.
1 million, 1 zillion, $1 trillion question.
So Z-axis will be there. 90x plus में वो Z-axis पे चलेगा.
Okay, you do a 90x pulse. This is the x-axis. This 90 not do anything with them, right? The only thing which will happen would be with this, right? And this will go
Minus
negative what? इसको भूल जाए, इसको don't. Now if you record the NMR spectrum, would you be able to see the big peak of C13 or not?
No.
It's amazingly simple. Very, very simple experiment. You see how related your doublet of C13 satellite from the big peak of isolated C13. And remember, having C13 as compared to C13 is at least 100 times. As I'm just comparing carbon 13 with carbon 13 with two neighbors as carbon 13. At least 100 times more. The peak of isolated 100 times more abundant as C13 satellite peak. Okay, and now I invite you to think over it. It's extremely simple. You convert longitudinal magnetization vector into a transfer magnetization vector. You give a tau delay. It is split into three signals. The center signal, which is the frequency of your rotating frame of reference, in order to understand that, it is the C13 because it has no C13 as a neighbor, a big peak of isolated C13. While the small satellite peaks represent a C13 which has a C13 as a neighbor. So it is split into a doublet, and doublet is counter-rotating. Again, the same philosophy that the neighboring C13 is either alpha or as beta. So this is a slower moving and this is the faster moving. And slowly they move away from each other. Slowly they move away from each other and they become antiphase. Antiphase. This is a mature situation in which you can separate them from this. Right? What you would do? कौन सा pulse देना चाहिए which will eventually take this strong component out of the system? 90x pulse. The 90x pulse will not do anything with this. It will just take it to the. And remember, when it is on Z plane, it is not observable. Therefore, what you see at the end of this experiment of the satellite, right? And a smart experiment. नहीं? It's so easy, but it's so exciting, extremely exciting. Now, I want to say that I want to detect the big peak also, because big peak is also important for me. I want to understand C13 coupling, and I want to have a chemical shift of isolated C.
It's in 90x.
And you bring it to, when you bring it here, when you turn on the detector, what a doublet on positive phase,
And minus
or a doublet on one phase, and
singlet on another phase.
okay. So it's so trivially simple, but it's an extremely exciting experiment. And you see the dilution of the natural abundance is 1 into 10,000. Having two C13s together, in 10,000, right? Having one C13 is 1 in 100, right? So kindly always remember that if you want to see the satellite peak of carbon-13 coupling with the carbon-13, you need to separate this big peak which belongs to isolated C13. This is the ultimate of NMR spectroscopy, but it's impossible. The quantity of sample required to record in spectrum like this is, you would need to have at least 500 milligram of a sample to record an inadequate experiment. 500 milligram of a sample, very often. Question is whether you solve 500 milligram. So you can have 1 ton of compound, but it can only take that much which solvent can dissolve. By a number of problems. Number one, dilution of spin, 2C13 together, 1 in 10,000, right? Much worse than natural abundance of 1 carbon-13. And you need lots of sample, and this lots of sample requires solubility, a perfect solubility, a suitable solvent. Always kindly remember, when we say solvent, it means suitable solvent, because very viscous solvent will not give you anything. Viscous solvent have a very high T1. As a result, the peaks are extremely broad. So you need to have a non-viscous solvent. A non-viscous deuterated solvent in which you can dissolve decent quantity of your sample, and then you run experiment for 26 hours to 36 hours. From 2 days to 3 days, from 1 day to 2 days, for a long period of time. You record so many skein, at the end of the day you get a spectrum in which you see only the carbon-13 couplings. And remember, it is really worth trying if you have a sample in good quantity. Now there are now many versions of this available. I want to ask you a question. I have been trying to, that polarization transfer is a very good thing. Tell me, can polarization transfer help in a situation like this? Question है, बिल्कुल simple सा question है, that you have a great problem of sensitivity. You have a problem ratio of carbon fourth of proton, and you have a problem that having is 1 in 10,000. Polarization transfer situation. Now you have to think like NMR spectroscopist. You have to think spectroscopist. You're trying to do a very dilute isotope of carbon-13. Sensitivity is absolutely miserably low. What can you do? can you, before doing anything like this, polarization transfer?
Of course, sir, we would do it.
Absolutely. I mean, that is what you do. You would use your skill of polarization transfer, and you do everything else. I invite you to think over this. This is your magnetization after polarization transfer. After you have done this by using ENaPT or whatever, polarization transfer. This signal is at least 4-fold better than a non-polarization transfer signal. And therefore, at the end of the day, you would get a greater sensitivity because you are starting with a greater sensitivity. So, what I am trying to convince to you that polarization transfer is not an isolated experiment. It can be built into multiple experiments, into a whole range of experiments as you build the spinico pulse. This 180 pulse is nothing but a spinico pulse. Right? As you build APT, attached proton test, in order to distinguish between multiplicities. So what we are trying to discuss a month or so is to let you familiar with the most experiments which become the part of the overall symphony of NMR, which become the part of the overall sequences of NMR spectroscopy. Polarization transfer is now used in almost everything in which carbon sensitivity is required. Do a polarization transfer experiment before this, and then you do the rest exactly identical manner. And if you want to, so there are plenty of different types of now built into sequences, and these pulse sequences become very efficient. Inadequate is an excellent technique in which you can read carbon-13 coupling directly. In a normal NMR routine, you always read proton-proton coupling first, then proton-carbon coupling, and then you indirectly connect carbon. That's how you elucidate the structure. You elucidate the structure by first recording proton-proton, then proton-carbon, indirectly couple the carbon attached to the proton. So, but if you can somehow record the carbon-13 coupling, this is the best thing one can do. Now, the good thing is that inadequate, which was initially developed as a one-dimensional technique, is now a two-dimensional technique, and I would revisit the entire concept again of inadequate, about the two-dimensional inadequate. Nobody is now doing one-dimensional. Everybody use two-dimensional inadequate, and we'll come back to this, but I wanted to give you the flavor of various types of one-dimensional NMR spectrum. Now, revisiting the whole thing, what we have, one pulse to the proton give you proton NMR spectrum. One pulse to the carbon will give you a broadband, will give you a fully coupled C13 NMR spectrum. Broadband decoupling will give you a broadband decoupled carbon-13 spectrum. Off-resonance coupling will give you long-range coupling eliminated. Resonance experiment will give you a spin, right? APT will give you multiplicities of the signal. Polarization transfer increase the sensitivity of your signal. Polarization transfer connected with the APT will give you the multiplicities of Polarization transfer increase the sensitivity. APT attached to polarization transfer will provide you intense signal with multiplicity information. You have a DAPT spectrum, which is a variant of it. Using a ADAPT, you can distinguish between quaternary carbon, proton, CH, CH2s and CH3s. Now, and then you have an inadequate. This is more or less what one-dimensional NMR spectroscopy is. This is more or less what you can do with the NMR spectroscopy, with the exception of NOE. NOE is still a one-dimensional NMR spectrum used, but I don't honestly. I don't like one-dimensional NOE. I like two-dimensional NOE. Therefore, I just kept NOE into two-dimensional. What are the major one-dimensional NMR experiment? Proton NMR, fully coupled C13 NMR spectrum, off-resonance C13 NMR spectrum, broadband decoupled C13 NMR spectrum, APT NMR spectrum, polarization transfer C13 NMR spectrum, polarization transfer with APT spectrum, ADAPT, additive polarization transfer experiment, inadequate spectrum. These are that's all, you know. That is what you have in the proton NMR spectrum. One-dimensional proton NMR spectroscopy is more or less this one. You know. वो इंशा जी कहते थे बस ये इतनी सी है, इतना ज़्यादा नहीं है इसमें, ठीक है? I want you to memorize this. थोड़ा सा आप लोग भी मेहनत करें. आज मैं सर में दर्द होने के बावजूद भी I'm trying my best. One-dimensional NMR experiment. God, इससे पता ही चलता है कि किसको कितना आता है. इससे पता चलता है सब बोल रहे हैं. कुव्वत गोयाई का पता चलता है. एक एक करके. एक एक करके.
उधर से शुरू करें. उधर से शुरू करें.
उधर ही पूछें. हाँ. प्रोटॉन NMR, right? प्रोटॉन सीक्वेंस बताइए जल्दी से. सिंपल प्रोटॉन NMR. And then नहीं, आपको कुछ मेहनत करनी पड़ेगी आज. You know, आज मेरे सर में दर्द है तो I want to make sure that you also have the same, right? प्रोटॉन NMR spectrum. पर सीक्वेंस बताइए जल्दी से. 98 then reduction. हाँ? दूसरा बताइए. Carbon 13. Couple carbon 13 per sequence. Expert of it now.
90 experts.
Fully coupled carbon 13 NMR spectrum per sequence.
90 experts.
जिसने सही बताया वो एक कूलर साथ लेके जाएगा. क्या ऐसे होगा? Okay. Fully coupled C13 NMR spectrum. कोई भी अपने आप को वॉलंटियर कर दे, मेरी जान छूट जाएगी. Fully coupled C13 NMR spectrum is just one pulse, 90 X pulse. That's it. Fully decoupled C13 NMR spectrum. What are the broadband decoupled proton carbon 13 NMR spectrum? Radio frequency oscillation on the frequency of proton and 90 pulse to carbon 13. That's it, finish. APT, attached proton test. 90 X pulse and then delay and then detection. ठीक है? Polarization transfer, source nuclei, SPI inversion, 180 X pulse to carbon 13.
And then
90 Y pulse to carbon 13, you record the carbon 13. Right? Inadequate.
so 90
X pulse,
180 Y pulse.
delay,
180.
90 Y pulse. आता है ना, I'm so surprised, you know, ये fresh होगा शायद ये सारे, yeah, ये, oh God. Okay, inept, inadequate.
सर पहले इनेप्ट वाली फिर इनएडिक्वेट वाली.
पहले inept कर ले फिर inadequate कर ले, सबसे आसान आंसर है ना. Okay, so this is more or less what one-dimensional proton NMR spectrums are. Solve many problems at the same time. You're trying to solve the problem of sensitivity. You're trying to solve the problem of interpretation, right? Interpretation की problem भी आपने solve की थी ना? किस में आपने interpretation की problem solve की थी? Which was the technique which solves your problem of interpretation? You were having difficulty in interpreting an NMR spectrum. So which one? Inept has nothing to do with it. No, inept is actually for sensitivity enhancement. Which particular experiment?
Depth.
Fully decoupled. Broadband decoupled carbon-13 spectrum solves your problem of interpretation. And what problem it created? Lost the multiplicity. In order to have a lost multiplicity, again obtain what you have done? APT. Sensitivity remain very poor. Done.
Polarization transfer.
Even in polarization transfer, you had problem of distorted signal. What you have done? That distortionless enhancement. You wanted to read carbon-13 satellite. What you have done?
Inadequate.
You add the inept with the God. You are just so intelligent. वो कौन सा है? वो कौन सा गाना है? चले उसको वो भी नेशनली टेलीकास्ट होगा, प्रॉब्लम होगी. One-dimensional NMR is literally what it is. Okay, not much exciting NMR spectroscopy. Essentially, you bring your magnetization vector from longitudinal to magnetization vector. Essentially, you give delays. You provide spin echo pulse to solve the problem of magnetic inhomogeneity. You can transfer the polarization by a 90Y pulse, right? SPI pulse. So there's not much in the theory of one-dimensional NMR spectrum. And believe me, one-dimensional NMR spectrum contain all the information. See, you have a fully coupled C13 NMR spectrum, will have information about direct coupling, would have information about the long-range heteronuclear coupling also. Normal proton NMR spectrum would have all the information about the vicinal couplings, homoallelic couplings, allelic couplings, W couplings. Everything is there. हर चीज उसमें होती है. You try to solve the problem of sensitivity by lots of interesting things. Hardware improvement, data manipulation, polarization transfer, pulse Fourier transformation, NMR spectroscopy. You have done lots of it. And then you must be a happy person. But this is what you get. This is the one-dimensional NMR of a protein. And the carbon-13 would not that be so different too, because this carbon-13, this proton, this protein contains, let's say, about 1,000 different carbons. You have done everything, you know. You tried your best to improve the sensitivity. You have done you carried out polarization transfer. You introduced the pulse Fourier transformation NMR spectroscopy. You sometime coupled, you sometime discoupled, you carried out a double resonance NMR spectroscopy, you have done selective ENaPT, you have done ENaPT, you have done DaPT, and you have done inadequate everything. You have done everything, and at the end of the day, this is what you get. A one-dimensional proton NMR spectrum of a protein. Now, try to solve this. Maldi से क्या होगा? Maldi will give you the structure. Sequence of structure. That's a very good proposal. ठीक है, fine. I agree with it. You would get a sequence, but sequence of a protein is not the structure. Always remember, it's nothing, because sequence you can do even without Maldi. There's a chemical reaction, you chop off your protein by using different hydrolytic enzymes, so you get a sequence of everything, right? So sequencing, Maldi doesn't really require to provide you de novo sequence. It's not a choice of, it's not a technique of choice for sequencing. This technique of choice for sequencing is which requires lots of hydrolytic enzyme, and structure of a protein is the structure of a protein. And the structure of a protein is a dimensional structure of a protein. Structure of a protein means configuration, spatial arrangement, hydrogen bonding, everything else. So this is your C13, this is your proton NMR spectrum, and that is what people have actually faced with. And then by solving the problem of interpretation. Can you, any one of you can say that this particular NMR, proton NMR spectrum of protein is lacking any information? Absolutely not. For instance, I can this peak which are down, which are off field than zero means a lot. What it means? You know, which proton would come below zero? Shielded. And can you find any shielded proton in a single sequence? You would never be able to find a shielded proton which is so shielded. These protons are belong to a propane region. Right? Only cyclopropane proton come below zero, or a metal just shielding to that level. This shielding because of a single fact that they are not one, but they are two helical structure which are immersed with each other like a DNA helix. And when they have a helical proton, they would appear as so a field signal. So every possible information. For instance, this will tell you that this protein must contain some aromatic amino acid. Right?
Yes.
Which are the most abundant aromatic amino acids? कौन से? Phenylalanine and tyrosine and okay. This region, this particular region, and which are the amino acid which have olefin, a carbon-carbon double bond? Huh? Histidine. Which amino acid which has a peptide bond, alpha proton bond of carbon. So many. Every one of it has a chiral center, and this most of them has a chiral center, and the chiral center, the CH proton would appear here also. And you would also have many peaks. This amino acid which have a methyl in them, right? These amino acids belong to CH2OH, And these amino acids are the ones which have a SS, so-called disulfide linkages. Every information which you can think about the sequence, conformation, helical structure, even to the dynamic of a molecule is present in this particular NMR spectrum. Problem is that you can't read it. The problem is not the lack of information. Problem is not that information is not there. Every possible information is there. For half an hour, what these different things are. I can tell you that these regions belong to a different types of aromatic. There are NHs. You know that there are amino acid with NH, and this NH would come in an amide bond. NH would come in this region. So there are plenty of different types of which are available in this particular proton NMR spectrum. Problem is that you cannot interpret it. So when people have solved the problem of sensitivity, they're faced with the problem of interpretability. This was the dilemma of NMR spectroscopy, that from 1946 to 1970, struggling to improve the sensitivity of a technique, and back in early 70s they realized that despite doing all of it, it is the interpretability which is a problem.
Interpretability is enhanced by resolving this spectrum, or
It's resolving the spectrum.
by resolution.
Interpretation means to recognize these peaks and should be able to extract information from this. Information exists, very sensitive. If you record the spectrum of this protein, that you would have 1,000 or more carbons. Selectivity is greater, from 1 to 220 you would have lots of these carbon, but even those carbons would have lots of overlap and you would not be able to interpret them properly. So it become a major problem once people have actually solved the problem of sensitivity. Sensitivity was partly solved by hardware. Sensitivity was partly solved by data manipulation like apodization. Sensitivity was partly solved by using techniques like pulse Fourier transformation, by using novel techniques like polarization transfer, but at the end of the day you get an spectrum which is sensitive spectrum, because you get all the peaks here. Nothing is hidden, everything is here. But question is that you cannot interpret that. Now, when somebody has seen the spectrum like this, the response was that this spectrum is primarily a one-dimensional spectrum, right? There is a spectrum which you are looking towards from the front. You are watching these peaks from the front, right? You are standing here and you are watching it. This is a one-dimensional spectrum, although this is not one-dimensional because you also have intensity, integration also, but that is not counted in NMR spectroscopy. In NMR spectroscopy, counted as a dimension. Please remember. And the time is counted as a dimension also. Integration is never counted as a dimension. Only the frequencies, either chemical shift or coupling constant in hertz, and the time is regarded as the. Now, so the first reaction of Gina, if we can somehow, these are the mountains-like peaks. There are lots of peaks in front of us, and there are lots of overlap. And because of this overlap, we cannot interpret this. And what you do when you see the mountains from the front, you see all the mountains in one dimension. You see one mountain after the other mountain, you see them peaks going in front of each other. You don't know which mountain is big, which mountain is small, you just see them in one dimension. The immediate reaction was that if we can add a frequency, or we should be able to see these peaks from upside down, as you see the mountains upside down. So you go up. If you go up and see the mountains from upside down, from an helicopter or plane, you would be able to see these mountains one after the other. You would be able to see that this mountain is so big, this is here, this mountain is here, this hill is here, this peak is here. You would be able to see, and you would be able to see them as a contour, not as a big peak, but you would be able to see them as a contour. You would be able to see the peaks like this. So the second dimension was a very obvious reaction of a very smart man, and he presented this lecture, a small workshop in California, UC Davis. Gina presented the idea of two dimensions. He said that theoretically it is possible to add one more frequency domain and to look into this, to spread this information in 2 dimensions. You know, when you go up on the mountain, you spread the information in 2 dimensions. You go, you see it from the upside down, you see all these because you have added 1 dimension into your visibility. So this was the idea which was presented, and people didn't really know what he was talking about. He was never appreciated, but he actually gave this seminal idea of the 2-dimensional NMR spectroscopy. And this 2-dimensional NMR spectroscopy is an amazing development. This was the first of it. 1978, the 2-dimensional NMR spectroscopy was routinely available on most of the NMR spectrum. The first spectrum which was introduced was correlated spectroscopy called COSY, and later they started introducing NOESYs and other. Inverse NMR spectroscopy came in early 90s, and you know, all of it. But this whole concept of adding 1 dimension was of seminal nature, was of extremely important nature. You see, in 1-dimensional NMR experiment, you give a pulse and then you record after certain delay or immediately. All of these scans, all of these experiments are exactly identical. They all are same. You do the same thing again and again, and you record the FID. In 2-dimensional NMR spectrum, there is only 1 variant. And this 1 variant is very, very interesting. For instance, this 1-dimensional time domain in 1-dimensional. You have a radio frequency, you detect it, you record the frequency, you record the free induction decay, you have a Fourier transformation, you record the proton NMR spectrum, or frequency domain. In the 2-dimensional NMR spectrum, there was one period were introduced which is called evolution period. Evolution time. This is the second time which is introduced. This is a delay between the preparation and recording. Don't be confused with the mixing time, because there is also a fixed time. Don't worry about that.